This is about the combined gas law. We've looked at relationships between pressure and volume, between volume and temperature, between pressure and temperature. And sometimes more than one of those things changes. So for any particular sample of gas, if we got the same number of moles, so we don't lose or gain any gas, um, and we change the conditions, pressure, volume, and temperature, we can, if we know the initial conditions and we know two variables on the final conditions, we can find the other variable. And so here's the equation for this. And we use these subscripts to represent one means before the change, two is after the change. So time one, time two. So we take pressure times volume divided by temperature. Remember, temperature is always has to be in kelvins. And here we've got pressure times volume equals temperature, but those are after. So here's how this works as an example. If I initially have a gas at a pressure of 12 atmospheres, a volume of 23 liters, and a temperature of 200 kelvins, and then I raise the temperature to 300 kelvins and the pressure to 14 atmospheres, what is the new volume? So you see, this is different from the problems we've done before because we're not just raising the temperature or raising the pressure, we're doing both. So if I'm writing out what my givens are here, pressure one, it says 12 atmospheres. Volume one, 23 liters. Temperature one, it's already in kelvins, so I can just directly put the 200 in here. If it were in Celsius, I'd have to add 273. For pressure, for after, let's see, 300 kelvins. And then the 14 atmospheres. And so then that makes volume my unknown. So you could always, when you have a combined gas law where you've got a changing situation with the gas, you can always set up, these are always going to be the variables, just like with the ideal gas law, it's always P, V, and RT. And so then there's always one that you don't know. So we need to know 5 out of these to find the 6th one. All right, so I've got my givens, my unknown, my equation, so now I'm going to substitute. So at this point, I've substituted in my pressure, volume, temperature, and what I do, I just don't put units here. I find it gets a little bit cluttered. There may be a different class with a different teacher who always wants you to include units for a past or future science course. For me, I think that if I can keep track of things and I'm setting things up correctly and in an organized way, then I can leave the units off here. And I know whatever happens, if I do this correctly, my volume will match the units from before, so my final units will be in liters. All these other units are going to cancel out. So to solve this algebraically here, I'm going to tell you a little trick to do that you may not be able to do in your math class because it doesn't promote understanding of what's going on, but it works. And so I don't know if some of you may have done this before, but you can just do a kind of a cross multiply here. And so we're going to take the 12 times the 23 times the 300 and set that equal to the 200 times 14 times V2. And so doing that, it eliminates the fraction. So using cross multiplication, I did the numerator here times the denominator here equals the denominator here times the numerator on the right. And like I said, if I were a math teacher, I might not want you to do it this way because it doesn't give any insight into the mathematics here, but it works. If I were teaching math right now, I'd probably want you to understand that more than just getting it right. Let's see. So I can multiply these three together to get 82,800, and multiply these together to get 2,800. Now I just divide both sides by 2,800, and we get about 29.6 liters for volume 2.